Usually when we talk about software, there is this ingrained expectation of documentation.
Right. Yeah.
Think about like a camera app on your phone, right? You point that camera at a mountain, you click a button, and the software just captures exactly what is there in that specific moment in time.
It's a literal recording.
Exactly. It documents reality. It's this one-to-one mapping of photons hitting a sensor to, pixels on a screen.
Yeah, the machine is really just analyzing the light that currently exists, processing that physical input, and saving it as a static file.
A faithful witness.
Right. The software is acting as a faithful witness to the physical world.
Exactly. A witness. But then, you step into the world of this new wave of artificial intelligence, and suddenly that camera is just gone.
Completely gone.
We are no longer talking about software that documents. Instead, we are looking at, a blank canvas and a digital paintbrush.
Yeah, that's a good way to put it.
We're looking at a technological landscape that isn't just capturing reality, It is actively dreaming up entirely new ones. And that shift, it changes absolutely everything about how we interact with machines.
It is the absolute definition of a paradigm shift in computing. We've moved from the machine as an observer, or even the machine as a calculator, to the machine as a creator.
That creator.
And the mathematics required to make that leap they're staggering.
And that is exactly why we are so thrilled to welcome you to this deep dive today. We are taking on the role of your personal guides, your instructors, really, as we navigate through this fascinating blueprint.
We are.
We are going to be exploring the concepts laid out in Chapter 6 of the ISACA Artificial Intelligence Primer. Now, if you are familiar with this material, or if you just, follow the broader landscape of AI, you know that historically, a lot of artificial intelligence has been about analysis.
Yes, very much so.
It has been about, taking a massive spreadsheet and finding the hidden trend, or looking at a medical scan and categorizing a cluster of cells.
Right, that's discriminative AI. It sorts, analyzes, categorizes. It takes a complex world and just applies a label to it.
Right. But the mission for today is singularly focused on the other side of the coin. Today is all about generative artificial intelligence.
Gen AI.
We are looking at AI that creates. We are no longer just asking the machine, what is this? We are asking the machine, make me a new one of these.
And that's a huge difference.
It really is. And reading through the research, looking at the capabilities of these models, it honestly feels like reading science fiction that has, it's quietly just become infrastructure.
It certainly looks like magic from the outside.
Yeah.
Especially when you see, a prompt turn into a photorealistic image in, 3 seconds?
Yeah, it's wild.
But our goal today is to kind of strip away that illusion. We're going to decode the complex mathematics and the intricate architectures behind this digital paintbrush.
So we're lifting the hood.
Exactly. We're going to break it down into understandable, logical concepts, because it is not magic. It's highly advanced, probabilistically driven mathematics.
Okay, let's unpack this. We're going to dive right into the mechanics of creation. So let's start at the very dawn of generative AI, or Gen AI.
Right at the foundation.
The foundational definition here is that this is a transformative branch of artificial intelligence with the specific capability to generate new and original content. And we aren't just talking about generating spam emails or simple text here.
No, the scope is massive.
Yeah. We are talking about generating high-resolution images, functional computer code, long-form text, incredibly realistic human speech, real-time language translations, complex musical compositions, and fine art.
To understand how a machine does this at a foundational level, we really have to look at the fuel it runs on.
Which is the training data, right?
Exactly, the training data.
Yeah.
This technology is fundamentally built on patterns. It ingests millions, sometimes billions of examples from its training data, and what it's doing isn't memorizing those files.
Okay, wait, it's not memorizing.
No, not at all. It is learning the statistical likelihood of certain elements appearing next to other elements. It learns the mathematical probability of, say, a specific shade of blue pixel appearing next to a green pixel in a landscape painting. Or, the probability of the word quantum appearing near the word mechanics in a physics paper.
So it's learning the rules of the game by watching millions of games being played rather than reading a rule book.
Precisely. In previous generations of machine learning, pattern recognition was the ultimate end goal.
Like the CNNs we'll talk about later.
Right. You train a model on 1 million pictures of cats, and it learns the statistical pattern of what constitutes a cat. It learns the shapes of the ears, the texture of the fur, the arrangement of the eyes.
And it does that so it can recognize the million and first cat that you show it.
Yes, generative AI takes that exact same pattern recognition and scales it up to pattern generation. It essentially runs the process in reverse.
How do you mean in reverse?
Well, instead of looking at pixels to determine if they represent a cat, the system says, I know the mathematical pattern of a cat so deeply, I can now construct a completely new arrangement of pixels from scratch that fits that pattern perfectly.
Wow.
The result is a high-definition image of a cat that has never actually existed in the physical world.
Okay, let me challenge you on that for a second, because this is where my brain always gets stuck.
Sure, go for it.
If this technology is essentially just looking at billions of past examples, absorbing those patterns, and then, spitting them back out, is it actually creating anything original?
That is the big question.
Right. Or is this just the world's most advanced remix machine? Are we just getting a highly sophisticated algorithmic collage of things that human beings have already made?
That is probably the most common and arguably the most important philosophical and technical question surrounding generative AI right now.
So what's the answer?
Well, to answer it accurately, we have to look closely at the math. We have to understand that it is definitively not a collage.
It's not.
No. It is not cutting and pasting snippets of its training data. When an AI model learns a pattern, it is not saving image files or text snippets into a database to retrieve later. It is learning a probability distribution.
A probability distribution. We hear that phrase a lot, but what does it actually mean in the context of, generating a piece of art or a block of code?
Think of it like learning the underlying concept of a melody rather than memorizing a specific song.
Okay.
A human musician who has listened to thousands of hours of jazz doesn't just play back exact snippets of Miles Davis and John Coltrane.
Right, they'd just be a cover band then.
Exactly. They internalize the mathematical relationships between the notes. They understand the probabilities of certain chord progressions evoking certain moods based on their vast training data of listening to music.
Right, they learn the structure of jazz, the scale, the swing, the expected tension and release.
Exactly.
Yeah.
And when you ask that musician to improvise a new solo, they are traversing a vast space of musical possibilities and selecting a path, a combination of notes and rhythms that has never been played exactly that way before.
That makes a lot of sense.
Generative AI is doing something incredibly similar, but in a mathematically rigid, multidimensional space. When you ask it to generate an image, it is not pulling a literal window from a photo of a house and pasting it onto a literal door from another photo.
It's not a scrapbook.
No. It is traversing a mathematical space of learned probabilities and selecting a combination of variables that has never been selected before.
So it's the specific combination, the pathway through the data that is new.
Yes. The foundation, the raw material, is absolutely derived from existing human-created data. The model cannot invent a completely new primary color that humans have never seen,
Right.
but the resulting combinations drawn from these learned probability distributions yield outputs that have never existed before. The mathematical arrangement is novel.
So it's original in its composition.
Yes. And because the resulting output is functionally indistinguishable from something a human might have spent weeks creating from scratch, it fundamentally pushes the boundary of what we define as original.
It's not stealing the painting. It's learning the physics of the paint, the texture of the canvas, and the psychology of the brushstrokes to paint something completely new.
That is a great way to summarize it.
That is a wild concept to wrap your head around. But to truly grasp this power, we can't just talk about it in the abstract. We have to look at the specific architectures that make this kind of creation possible.
We need to see how it's built.
We have to look under the hood. And that leads us directly to the first major model we need to unpack. GANs.
Ah, yes. Generative Adversarial Networks. Introduced by Ian Goodfellow and his colleagues back in 2014, this was a watershed moment in the history of artificial intelligence.
2014, so this isn't even that old.
No, not at all. But it was a completely new way to approach the problem of generation.
The ISACA material describes the GAN architecture as a dual network system. And I love this because it's not just one AI working alone in a void. It's two separate neural networks locked in a room together.
Locked in a very competitive room.
Exactly. You have the generator and the discriminator. And they are competing against each other in what is mathematically described as a two-player game.
It is a brilliant architectural design because it leverages competition to drive improvement. These two networks are trained simultaneously, but they have completely opposing goals.
Right. They hate each other.
Conceptually, sure. The generator's entire job, its sole purpose for existing, is to produce fake data that looks as real as possible. And the discriminator's entire job is to look at a piece of data and figure out if it is real, meaning it came from the original human-made training data set, or if it's fake, meaning it was created by the generator.
To help visualize this, let's lean into an analogy that perfectly captures this specific mathematical relationship. Think of it like an art forger and a police detective or, a world-class art judge.
That is the classic analogy for a Jan, and it holds up remarkably well to the actual mechanics.
So you have the generator. The generator is the art forger. They are trying to paint a fake Rembrandt.
Right.
And then you have the discriminator. The discriminator is the art detective trying to spot the fake.
Right.
Now, in the very beginning, on day one of training, the forger is terrible, right? They essentially paint a stick figure, slap Rembrandt's name on it, and try to pass it off.
Mathematically speaking, at the very beginning of training, the generator's neural weights are completely randomized. So it is essentially just outputting pure static.
Just TV static.
Just random noise. It has no idea what a Rembrandt looks like or what a face looks like or even what a coherent shape is.
Right. And the detective looks at this canvas full of static, looks at a real Rembrandt portrait, and says, this is obviously fake. This is just noise.
It catches the fake instantly.
But the forger doesn't just give up. The forger learns from getting caught. This is the crux of it. How does that learning actually happen under the hood? What does it mean for a mathematical model to get caught and learn from it?
This is where we get into the mechanics of the rivalry. The discriminator network is typically a convolutional neural network, or a CNN, which is highly optimized for analyzing images.
Okay, CNN.
When the discriminator catches a fake, that information doesn't just stop there. A signal is sent back to the generator through something called a loss function.
A loss function. That is a term you see everywhere in AI literature, but it rarely gets explained clearly.
It's crucial here. A loss function is a mathematical formula that calculates the error. It measures how far off a model's prediction or output is from the true desired outcome.
So it's like a grade.
Well, you have to understand, it's not just a simple score, like getting a 60% on a math test. It's a vector. It's a highly complex feedback mechanism that tells the network mathematically exactly how it was wrong. It calculates the gradient of the error, which in turn tells the generator exactly how to adjust its millions of internal weights to be slightly less wrong the next time.
So to go back to our analogy, the detective doesn't just hold up a red card and say, fake. The detective hands the forger a detailed report that says, I knew this was fake because the brush strokes in the upper left corner lack the specific chemical density of 17th century Dutch oils, and the lighting on the cheekbone doesn't match the angle of the window.
Exactly. It's hyper-specific feedback.
And the forger takes that exact, highly specific mathematical feedback, goes back to the studio, tweaks their formula, and figures out how to mimic 17th century Dutch oils just a tiny bit better.
Yes. And this happens over and over again. Through thousands or millions of iterations, the generator meticulously refines its ability to create data. The loss function acts as a guiding force, pushing the generator closer and closer to the statistical distribution of the real data.
But the detective is learning too, right?
Remember, the discriminator is also learning. As the generator gets better at forging, the discriminator is constantly analyzing more real data and more fake data, getting better and better at spotting microscopic inconsistencies.
It's an arms race. The fake Rembrandts are getting incredibly good. The brushstrokes, the lighting, the canvas texture, they all start to perfectly align with the real thing. But the detective is also getting a stronger magnifying glass.
Yes, and this leads to the ultimate goal of the system. Here is where the mathematical elegance of a GAN really shines. The system is pushing toward a state of equilibrium.
An equilibrium between the two.
A GAN is considered perfectly trained only when the discriminator is completely, hopelessly fooled.
When the detective can no longer tell the difference between the real Rembrandt and the fake one.
Right. In game theory, this concept is closely related to a Nash equilibrium. At this point in the training process, the discriminator is essentially just guessing.
Like 50-50.
Exactly 50-50. It is flipping a coin. It has exactly a 50-50 chance of being right because the data generated by the forger is now perfectly aligned with the statistical distribution of the real data. There are no more flaws for the discriminator to detect.
The forger has become so masterful that their work is mathematically indistinguishable from the master they are copying. That sounds like a perfect system. But if you dig into the literature on GANs, it sounds like reaching this equilibrium is, well, incredibly volatile.
Oh, it's a nightmare to balance.
It's not a permanent stable utopia.
No, it is notoriously difficult to maintain. If we extrapolate on the math here, maintaining that exact 50-50 equilibrium is like balancing a marble on the very tip of a needle. It requires absolute precision.
What happens if it slips?
Well, if the discriminator suddenly figures out a tiny flaw, say, it realizes that the generator struggles with the complex geometry of human hands, and the discriminator gets too good too quickly, the loss function might send signals back to the generator that are too extreme.
And it overcorrects.
Yes, the gradients become unstable, causing the generator's internal weights to spin out of control.
And what happens when it spins out of control? Does the program just crash?
You often see a known catastrophic failure called mode collapse.
Mode collapse.
This is a fascinating vulnerability. Mode collapse happens when the generator finds a loophole. It stumbles upon one single specific image, say a perfectly generated image of a brown dog sitting on grass, that consistently fools the discriminator.
Okay, so it found a winner.
Right. But once it finds that one perfect forgery, the generator essentially gives up on trying to learn anything else. It stops trying to paint cats or birds or white dogs. It just produces that exact same image of the brown dog over and over and over again, completely losing the diversity of the training data.
Because it optimized for the win condition, it found the one fake painting the detective always thinks is real, so it just mass produces that one painting. It's lazy.
Mathematically lazy, yes. It found a local minimum in the error landscape and decided to stay there. Training a GAN requires incredibly delicate tuning. You have to meticulously manage the learning rates and the architectural depth of both networks to ensure they improve in perfect tandem without one completely overpowering the other and causing a collapse.
Now, you mentioned a moment ago that the discriminator in this scenario is usually a convolutional neural network, or CNN.
Yeah.
And since we are breaking down the taxonomy of these models, it is the perfect time to clear up exactly how a CNN differs from the GAN as a whole. Because it can get a little confusing for someone trying to map this out when an AI model is actually made up of other differently named AI models.
It is an absolutely critical distinction to make. CNNs and GANs are both major subfields of deep learning, but their fundamental functionalities and mathematical objectives are entirely different.
Okay, how so?
CNNs are designed for discriminative learning. They are the sorters, the classifiers, the extractors of features. They look at existing data and assign a label or abstract a meaning from it.
So object recognition in images. You show a CNN a picture, it scans the pixels, and it says apple, orange, or carrot. Right.
Or speech-to-text conversion. You feed it an audio file, it identifies the acoustic patterns, and it types out the words. It is taking complex reality and reducing it to a category.
Exactly. A CNN works by passing data through layers of mathematical filters. The first layers might just look for sharp edges or contrasting colors.
The basics.
Right. The deeper layers combine those edges into shapes like circles or squares. And the final layers combine those shapes to say, a circle with a stem on top, that's an apple. It is breaking things down. Conversely, gens are generative.
They build things up.
Yes. Their objective is to create new, original, high-dimensional data that is nearly indistinguishable from the real data they were trained on.
Let me try a real-world analogy here to help visualize this difference in functionality. Imagine a massive, chaotic post office.
Okay, I'm picturing it. A convolutional neural network is like a highly trained postal worker standing at a conveyor belt. They can look at millions of envelopes rushing past, read the messy, scribbled handwriting, and instantly sort them by zip code. This goes to New York, this goes to London, this goes to Tokyo.
Right, they're sorting.
The worker isn't writing the letters. They are classifying existing information. They are discriminating between different inputs.
That is a perfect visualization of discriminative architecture.
But a generative adversarial network. The GAN is not the person sorting the mail on the conveyor belt.
No. Definitely not.
The GAN is the person sitting at a dimly lit desk in the back room, actually writing a brand new, highly convincing letter from a fictional person. They are forging the handwriting, putting a fake stamp on it, and dropping it into the mail stream to see if it passes inspection.
What's truly fascinating here, the beautiful irony of the architecture, is that while they are doing opposite things, one is a sorter and one is a creator, in the context of a GAN, they are deeply, inextricably complementary.
They need each other.
The GenN actually requires the discriminative power of the CNN to exist at all.
Right. The creator needs the sorter.
Yes.
Yeah.
Without the CNN acting as the harsh critic, acting as the discriminator, the generator would never learn how to create anything realistic. We have to remember, the generator is completely blind to reality.
Wait, it never sees the real data.
Never. It does not have access to the real training data. It has never seen a real photograph. The only window it has into reality is the numerical feedback it gets from the CNN.
Oh, wow.
It only learns through the CNN telling it, "You failed, this doesn't look like an apple, adjust your weights." The CNN forces the generator to achieve greatness through relentless critique.
So they are locked in this eternal mathematical struggle, the sorter and the creator, and the byproduct of that struggle is incredibly realistic, entirely new data, entirely new data. It is just a brilliant way to engineer a solution to a problem.
It is an elegant piece of engineering, but is also highly combative and, as we discussed, mathematically volatile.
Which perfectly sets up our next major concept. Because while Jans use this highly competitive game to create, there's an entirely different, highly mathematical way to generate new data.
A much less combative way.
Right. A method that doesn't rely on competition, adversarial networks, or trying to fool a detective. Instead, it relies on the principles of compression and probability. And that brings us to variational autoencoders, or VAEs.
This is a dense, mathematically heavy topic, and it represents a very different philosophy of generation compared to Jans. To truly understand a variational autoencoder, we first have to build a foundation by understanding a standard autoencoder.
Okay, so take out the variational part for a second.
Yes, we need to look at what they were trying to achieve before they added that.
Okay, let's lay that groundwork. What is a standard autoencoder doing?
Think of an autoencoder as a data compression algorithm that teaches itself how to compress data. It has two main components, encoder and a decoder.
Encoder and decoder. Got it.
You feed the encoder an incredibly rich, complex piece of data, say, a massive, high-resolution, uncompressed photograph of a forest. The encoder's job is to pass that image through successive neural layers, squeezing it down, stripping away all the raw pixels, and compressing it into a tiny, dense mathematical representation.
Like zipping a file.
Exactly. We call this compressed state the latent space, or the bottleneck.
So it's like taking a sprawling 1,000-page fantasy novel and forcing someone to write a strict 3-sentence summary that captures the entire plot, the underlying themes, and the character arcs perfectly.
That's a great way to think of it.
That 3-sentence summary is the latent space.
Yes. It represents the absolute most essential abstract attributes of the original data. Then, the second half of the network takes over, the decoder.
It unpacks it.
Right. The decoder takes that 3-sentence summary, that tiny latent representation, and tries to reconstruct the original 1,000-page novel, or in our case, the high-resolution photograph of the forest from it.
Can it actually do that?
Well, the network trains itself by comparing the final reconstructed image to the original input image. The objective is to make the reconstruction as close to the original as mathematically possible, minimizing the difference between the two.
So it's a closed loop. It's teaching itself how to perfectly compress and then perfectly decompress data, figuring out what information is essential and what information is just noise.
Exactly. And that is incredibly useful for things like reducing file sizes or removing static noise from an image. But here's the critical limitation. A standard autoencoder is strictly deterministic.
Deterministic meaning it operates on fixed, absolute rules.
Correct. When a standard autoencoder compresses an image of a specific person wearing a yellow jacket in a foggy forest, it maps the concept of that specific image to a single specific point in the latent space, a fixed set of coordinates.
Like a GPS location.
Yes. If you put that exact same image in 1,000,000 times, you will get the exact same point in the latent space 1,000,000 times. It is rigid.
Okay, I have my single point, a stripped set of coordinates. But we aren't talking about standard autoencoders. We are talking about variational autoencoders. What does the variational part add to the mix that changes this from a compression tool into a generation tool?
This is the crucial difference, and it requires careful instruction because it's a lead into probability. A variational autoencoder does not map a feature to a single rigid point. It maps it to a range of possibilities encapsulated in a probability distribution.
We are back to probability distribution.
Because it is the absolute heart of how machines generate novelty. Instead of the encoder saying the jacket in this photo is exactly the color value, 0.92, the VAE encoder says the jacket color is somewhere in this general region. It has a mean value of around 0.9, the standard deviation of 0.1.
Oh, so it's fuzzy.
It creates a bell curve of possibilities for every single attribute of the image.
Let's make this really concrete. Let's imagine compressing a photograph of a person standing in the woods. A standard autoencoder looks at the photo and gives you hard numbers. It says, human presence is 0.98. Jacket color is 0.92. Fogginess is 0.15. Animal presence is negative 0.99. It's just a rigid list of values.
Right. There's an exact recipe.
Yeah.
But a variational autoencoder looks at that same photo and learns that fogginess isn't just a static number. Fogginess is a property that can vary. It learns the distribution of fogginess across all the images it has ever seen.
So instead of memorizing the exact pixels of that specific yellow jacket in that specific lighting, the network essentially builds a control panel.
A control panel, yes.
It creates a slider for jacket color ranging from, say, Matic of 1 to 10, and another slider for fogginess from Matic 1 to 10, and another for tree density.
That is a brilliant way to conceptualize it. By turning these rigid, distinct attributes into continuous probability distributions into these sliders, we unlock the ability to generate entirely new things.
Because we can move the sliders.
Exactly. Because the latent space is no longer a collection of isolated dots. It is a continuous, mathematically smooth landscape.
Right.
We can go into that latent space, grab the fogginess slider, and just manually nudge it up. We can grab the human presence slider and turn it all the way down. We can slide the jacket color value slightly to the left toward the red spectrum.
And then we tell the decoder, okay, take these completely new slider settings that did not exist in any original photograph and decompress them back into an image.
Yes. And because the decoder has been trained to smoothly construct an image based on any point within these probabilistic ranges, it will generate a completely new image.
It actually works.
It worked beautifully. It will output an image of a slightly redder jacket in much thicker fog with no human visible in the frame. It generates new plausible data samples based on the probabilistic variable nature of the real world.
That is an incredible contrast to GANs. A GAN locks two networks in a room to fight with each other until reality emerges from the struggle. But a VAE acts more like an incredibly complex synthesizer. It builds a multidimensional control panel for reality, maps out the physics of the data, and just lets you play with the dials.
It's a very elegant, mathematically stable solution for capturing the continuous flowing nature of data. It ensures that if 2 points are close to each other in the latent space, the images they generate will also look similar. It brings a sense of topological order to the chaos of high-dimensional data.
So we've looked at GANs and VAEs, we've seen the adversarial game, and we've seen the probabilistic sliders. At this point, it's helpful to take a step back and codify everything we've learned so far.
Sort it all out.
Right. If you look at the broader landscape of AI, you can take all these incredibly complex models and sort them into two massive overarching buckets.
The grand division of contemporary artificial intelligence architectures: discriminative models versus generative models.
Right. And just to reiterate what we've touched on, because it is the foundational concept here, discriminative models distinguish between different types of data. Their job is to draw boundaries.
Yes.
Is this a picture of a dog or a picture of a cat? Is this credit card transaction normal or is it fraudulent? Generative models, on the other hand, generate new data. Their job is to understand the distribution of the data so well that they can say, here is a completely new synthetic picture of a dog that has never existed.
Exactly.
But why is it so important to explicitly state this taxonomy? Why do we need to firmly place these models into these two buckets?
Because you need to solidify your mental framework regarding the fundamental mathematical objective of a machine. A discriminative model's objective is to map an input to a predefined label. The equation ends at the classification. It reduces complexity.
Okay.
A generative model's objective is to map learned distributions to new synthetic outputs. The equation ends with creation. It expands complexity.
So what does this all mean for you, listening to this? If you are an enterprise professional, an IT auditor analyzing risk, a developer building a new app, or just a curious individual navigating a world suddenly filled with AI tools, why does this distinction matter to your day-to-day life?
It's highly practical.
It matters because knowing this distinction is the key to knowing which tool to pull from the toolbox for a specific real-world problem.
Absolutely. The business implications are massive. Let's say your company wants to automatically flag fraudulent transactions on a banking platform. You do not need and should not use a generative model for that.
Why not?
Because generative models are computationally heavy, expensive to run, and prone to hallucination. You need a highly accurate, ruthlessly efficient, discriminative model.
Right. You just needed to look at the data and say yes or no.
But if your marketing department comes to you and says they want to create 10,000 unique variations of an ad campaign with the images and copy customized in real time to individual user profiles, a discriminative model is entirely useless.
It can't draw the picture.
It cannot create. You need the power and the computational budget of a generative model.
Yeah.
Understanding this taxonomy is about aligning the underlying mathematical architecture with the desired business outcome.
It's about knowing the shape of the problem so you can choose the AI with the right shape of solution. It saves time, money, and a lot of frustration.
Definitely.
But what happens when the problem is everything? What happens when you want a generative model that doesn't just create images or classify numbers, but can actually understand the vast, chaotic, infinitely complex sequences of human language and then apply that understanding to almost any task you can imagine?
To achieve that level of generalized capability, you can't use a convolutional neural network. You can't use a GAN.
Nah.
And you can't use a VAE.
They just aren't built for it.
No, those are powerful, but they have architectural limitations when it comes to long sequences of data. You need a completely different revolutionary architecture.
And that brings us to the final and undoubtedly the most impactful architecture we need to discuss. The heavyweights. The models that are currently reshaping the global economy. Transformers.
The transformer model has completely redefined what humanity thought was possible with AI, and it did so in a shockingly short amount of time.
It really was fast.
It was initially designed by researchers at Google in 2017, specifically for natural language processing, or NLP. The goal was simply to handle language translation better, but its underlying architecture proved to be so robust, so inherently capable of mathematically understanding context, that it has evolved far, far beyond its original purpose.
Just look at the sheer variety of tasks this architecture handles today. We are talking about text generation, writing essays, drafting legal contracts, writing emails.
Summarization.
Yes, summarization, taking a 100-page technical document and giving you a highly accurate 3-paragraph bulleted summary. Question answering systems that can pass medical licensing exams. Sentiment analysis, ingesting 1 million tweets in real time and telling a brand whether public opinion is trending positive or negative.
And that's just text.
Right. Named entity recognition, highly accurate speech recognition, and incredibly code completion. We have natural language models writing functional, complex software in Python and C++ing.
To truly understand why the transformer architecture is so dominant, we have to look at what it replaced. We have to look at why the previous generation of models hit a brick wall.
What were they using before 2017?
Prior to 2017, the kings of sequence data were models like recurrent neural networks, or RNNs, and long short-term memory networks, or LSTMs.
And when we say sequence data, we just mean data where the order of the information fundamentally changes the meaning, right? Language is the perfect example. The dog bit the man means something entirely different than the man bit the dog. The words are identical, but the sequence dictates the reality.
Exactly. And the older models, like RNNs, process that sequence data linearly. They read a sentence exactly the way a human does, word by word, from left to right. They would process then update their internal state, then process dog, update again, and so on.
That sounds logical. Why was that a problem?
It created two massive bottlenecks. First, because it was sequential, it was incredibly slow to train. You couldn't process the end of the sentence until you had processed the beginning.
Makes sense.
Second, and more importantly, they suffered from a mathematical flaw known as the vanishing gradient problem.
The vanishing gradient. We talked about gradients earlier with the loss function. It's the mathematical signal that tells the network how to adjust. Why was it vanishing?
Imagine playing a game of telephone with 100 people. By the time the message gets to the end of the line, the original meaning is often lost or distorted.
Purple monkey dishwasher?
Right, exactly. In an RNN, as the gradient signal travels backward through a very long sequence, like a long paragraph of text, the numbers get multiplied together. If those numbers are small, multiplying them repeatedly causes the signal to exponentially shrink toward zero. It vanishes.
Wow, okay.
Practically, this meant that by the time the model reached the end of a long paragraph, it had literally forgotten the context of the first sentence.
It had terrible short-term memory. It couldn't connect an idea on page 1 to a conclusion on page 5.
Precisely. The transformer, introduced in the famous 2017 paper, Attention is All You Need, threw that sequential processing model entirely out the window. It doesn't read left to right.
So how does it read?
It processes the entire sequence simultaneously. It looks at every single word in a sentence or every single token in a document at the exact same time.
How does it manage to understand the sequence if it reads everything at once? That sounds like chaos.
Through a breakthrough mathematical mechanism called self-attention. Self-attention allows the model to mathematically calculate how much attention or importance each word should pay to every other word in the sequence, regardless of how far apart they're physically located in the text.
Let me see if I can map this out. Take a sentence like, I went to the bank of the river to eat my lunch, and another sentence, I went to the bank on the corner to deposit my money. The word bank is identical in both.
Right, a classic disambiguation problem.
But the transformer sees the whole picture at once. It calculates the relationship between bank and river in the first sentence and assigns a heavy mathematical weight to that connection, realizing it means a muddy shoreline. In the second, it calculates the heavy attention weight between bank and deposit, realizing it means a financial institution, and it figures all of that out instantaneously.
Yes. It builds a dense, multidimensional web of context. It maps the relationships of everything to everything else simultaneously.
That's brilliant.
And because it processes everything at once rather than sequentially, it is massively parallelizable. You can train a transformer on clusters of thousands of graphics processing units or GPUs at the same time. You can feed it unprecedented amounts of data. This architectural leap is what made the era of foundation models possible.
Foundation models. This is the term that really defines the current era. These are models trained on massive, almost incomprehensible amounts of diverse and general data sourced from across the entire internet. We are talking about feeding an AI architecture essentially the entirety of Wikipedia, millions of digitized books, decades of news articles, massive repositories of computer code like GitHub, essentially the collective digital knowledge of humanity.
And this is where we see the all-star team of AI products that are currently dominating the cultural conversation. They are all built on the transformer architecture.
It reads like a who's who of the tech world right now. You have ChatGPT from OpenAI, you have Gemini from Google, Claude from Anthropic, Llama from Meta. You have open source powerhouses like Mistral AI and Falcon.
And they keep evolving.
And it's not just text anymore. The fundamental mechanisms of the transformer have been adapted to handle multimodal generation. You have models like DLE, Midjourney, and Stability AI generating astonishing images. You have 11 labs generating synthetic voice that captures breath and emotion. You have Runway generating actual video from text prompts.
If we connect this back to the enterprise level, the reason these foundation models are so ubiquitous and so valuable is because of a concept called transfer learning.
Transfer learning, what is that?
Because these models are trained so broadly on essentially everything humanity has ever written, they possess a foundational, generalized understanding of language, logic, and structure. They have unparalleled flexibility.
So if I want to build an AI that helps doctors diagnose rare diseases, I don't have to start from scratch. I don't have to spend millions of dollars training a model on basic English grammar before I can teach it medicine.
Exactly. You take a massive pre-trained foundation model that already understands English grammar, logical reasoning, and basic science perfectly. Then you simply fine-tune it. You take a much smaller, highly curated data set, say 50,000 peer-reviewed medical textbooks and anonymized patient records, and you train the model on that specific data for a short period of time.
The model transfers its vast general knowledge to this highly specific narrow task.
Yes. This is why transformers are simultaneously disrupting healthcare, finance, corporate law, software engineering, and creative writing. The foundation of intelligence, or at least the simulation of it, is already built. We were just customizing the specialized structures on top of it.
Okay, that phrase you just used, the simulation of intelligence, brings up something really profound that we need to address. There is an article by the physicist and computer scientist Stephen Wolfram titled, "What is ChatGPT doing? And why does it work?"
It's a great read.
It is. And when you read about how these transformer models actually operate, how they are essentially just predicting the next word based on massive data sets, it creates a cognitive dissonance. Because I sit there and I have deep, philosophical, highly nuanced conversations with Claude or ChatGPT. It feels like it understands my nuance. It feels like it gets my jokes. It pushes back on my logic.
It's very convincing.
But if it is truly just doing math, if it is just looking at the previous words in the sequence and calculating statistically the next most likely word is apple, does it actually understand us? Or are these transformers just the ultimate illusionists? Are they just performing an incredibly complex parlor trick that mimics human comprehension?
That is the defining debate in cognitive science, philosophy, and artificial intelligence right now. From a strict mathematical, architectural perspective, as Stephen Wolfram outlines beautifully, it is simply next token prediction.
Next token prediction.
It is a highly complex, multi-dimensional probability matrix calculating the most likely subsequent piece of data to output. It does not have a mind, as we understand it. It doesn't have lived experience. It doesn't have consciousness. And it doesn't have internal intent.
Right. It doesn't know what an apple tastes like. It doesn't know what the color red looks like. It just knows that the token for apple is mathematically clustered very closely to the tokens for red, crisp, and fruit in a high-dimensional space.
Correct. However, what is truly fascinating, and what AI researchers are still actively grappling with, is the phenomenon of scale.
What happens when it scales?
When you take that simple mechanism of next token prediction and you scale it up to models with hundreds of billions of parameters and you train it on trillions of words, something happens that looks remarkably like emergent reasoning.
Emergent reasoning, meaning it wasn't programmed in, it just appeared as a byproduct of the scale.
Exactly. Think about it this way. To accurately predict the next word in a highly complex logical puzzle or a complex piece of Python code, the model cannot simply rely on basic statistical frequency. It essentially has to internalize the underlying rules of logic to guess the next word correctly.
That's mind-bending.
It has to build an internal, abstract representation of the world of physics, of human psychology, purely to solve the mathematical problem of language prediction.
So by forcing it to perfectly mimic human language, by forcing it to predict the next word in every conceivable scenario, we accidentally forced it to mimic human reasoning.
It is mimicking the structure of human reasoning as it is embedded within our language. Whether that mathematical mimicry constitutes true, conscious understanding is a philosophical question that we may not answer for decades.
Yeah, that's a whole other deep dive.
For sure. But functionally, practically, the result is an artificial intelligence that can pass the bar exam, debug complex server architectures, summarize vast amounts of data, and write poetry that evokes emotion. The illusion of comprehension is so perfect, so statistically sound, that for many practical, real-world applications, it becomes entirely indistinguishable from actual human comprehension.
That is both awe-inspiring and, honestly, slightly terrifying. It really brings home the magnitude of what we've been discussing today. We are not just building better calculators anymore. We are building massive mathematical engines that can hallucinate our reality on command.
It is a profound shift in the trajectory of human technology. And understanding the distinct architectures, the competitive nature of GANs, the probabilistic nature of VAEs, and the attention mechanisms of transformers is critical to navigating what comes next.
And with that, we have reached the end of this incredibly dense, fascinating blueprint. I want to thank you for joining us on this deep dive today. We have covered an immense amount of ground.
We really have.
We started with the dawn of generative AI, defining the massive shift from models that merely analyze to models that actively create. We looked deeply into the adversarial competitive games of GANs, where the digital forger and the detective battle endlessly to create perfect synthetic data.
The arms race.
We explored the complex probability sliders of variational autoencoders, manipulating the latent space to smoothly bend and mold reality. And finally, we arrived at the massive, multitasking, world-eating power of transformers, self-attention, and foundation models.
It is a vast amount of complex information to process, but understanding these architectural foundations, understanding the difference between how a CNN sorts and a GAN creates, is absolutely critical for anyone trying to navigate the technological and economic landscape that is unfolding around us right now.
And as we close out this deep dive, I want to leave you with a final lingering thought, something to really mull over.
Always good to end on a question.
We talked about GANs achieving that perfect Nash equilibrium where the detective is completely, hopelessly fooled. We talked about transformers generating text and code that is entirely indistinguishable from a human expert. As these generative AI models become perfectly integrated into our daily tools, into our word processors, our search engines, our design software, will we eventually just stop caring whether a piece of content was made by a machine or a human being?
That's the million-dollar question.
If the article is highly informative, or if the art moves you to tears, will the origin of that creation even matter to us anymore? Or, conversely, will the sheer, overwhelming abundance of infinite, instant, AI-generated content make verifiable, authentic, human-made art, writing, and code more valuable and cherished than ever before in human history?
It's a profound question, and it's one that goes far beyond computer science. It strikes at the heart of sociology, economics, and what it means to value human effort.
It really does. Keep observing these architectures out in the real world. Every time you see a customer service chatbot, a stunning AI-generated image, or a piece of synthetic voice acting, you now know the mathematics humming beneath the surface.
You know the magic trick.
You know if you're looking at the result of a competitive game, a probabilistic slider, or a massive parallelized web of attention. We are signing off from this deep dive for now, but remember our opening thought. The software camera has been put away. We are officially in the era of the digital paintbrush. Have a great day.